Hello everybody, my name is Josh. I was a computer science examiner for a really long time for multiple exam boards, head of computer science in UK based schools, and now I run a tutoring business where I've helped thousands of students to get better grades in computer science related courses. And what I've been doing with these series of lessons is trying to condense all of the information down that you need to know using my examiner knowledge, so that you've got it in a bite-sized chunk that is going to simplify your revision. And today's lesson is all to do with data structures, and this is a big unit which is relevant for all specifications. I'm going to do a part 1 and a part 2. This one is relevant for every single specification. The part 2 is going to be relevant for, I'm going to make that specific to the exam boards, because for example on AQA you have to know about vectors, OCR you don't, so I'll go through and start doing the rest of those so that then you've got every single data structure in there. Now we're going to do queues, stacks, hash tables, trees, and graphs. We're going to do all of those today. So first one is queues. It's going to be in this format. What the item is, some of the different features about how to add, search, delete data from it, the pseudocode or programming code around that, and then an example of how it all fits together. So queue, first flashcard is what is a queue. An abstract data type that is a FIFO data structure, first in, first out. If it's the first item in there, it's the first item to exit it. You use a list in Python to implement this, and you add items to the back of the list. This is used in real life examples of print queues and uploading lots and lots of images if you had to do those in order. Now, the thing that it specifically says in the specification is how to add items, how to remove data if applicable to the particular data structure, and then also how to search it again if applicable. So adding items is enqueuing. So what this does is this checks to see if the queue is full first, and then what it is going to do is then going to add one to the rear pointer. Okay. How do we remove data from a queue? What happens is we dequeue, so that's a mark in itself, check if the queue is empty, return the value pointed by the front pointer, so I should say pointer, and then increase the front index by 1. Now, with all of this, I've used my examiner knowledge to essentially look at all of the different things the styles of questions that could come up. They could ask you to describe like this, and they could ask you to write programming code, which I'll put in the next slide. I'll go through everything, and then at least you'll have a really, really good understanding of each data structure. It also says about advantages and disadvantages of each data structure. Plus, it's easy to implement. Minus, when I start talking about circular queues, because this isn't circular queues are not relevant to Cambridge International, is being able to delete and insert values that are in the middle. That can be quite time consuming. This is the pseudocode, or sorry, I should say the Python actual code for enqueuing and dequeuing. So enqueuing is the code which adds items to our queue. The first check is our queue full. So if that's full, we need to output to the user that the queue is full and not enter anything into there. Then we're going to use the append function in Python to add the item to it. Dequeue what is the opposite, where what it does is it removes something from the front of the queue, and you'll see that we've actually got a function called pop. Pop naturally works, which we're going to see works with stacks, and it will output the last item in the list. But if we put 0, that is going to be the position 0 in pop, so the first item in there, and that will continually keep outputting data from the front of the queue, which is how we want the queue to behave. And then we just need to -1 from the size of it. We also obviously have to check and see if the queue is empty, because we don't want to remove anything from a queue that is an empty list, because that's impossible. There are a number of ways of doing this with the if statement. You can also look to see if the rear pointer is -1. When a queue is initialized, the queue is what happens is the rear pointer is to -1. Now, the final kind of style of question that you could potentially get is where they just get you to follow a load of different operations that are happening to the queue. Now you can see when we've initialized it and we use the operation isEmpty, we've got an empty list here, empty array I should say. And what we've got here is we've got that the size is equal to 0 because there's nothing in it. The rear is set to -1 and the front is 0. And this is going to return true because there isn't anything in there. We add y and add m to it. So we put y and m in there. And then what happens is the size changes to 2. The rear is going to change to 1 because m is in position 1. Remember, computers start from position 0 and then go to 1. Front is still going to be 0 because that's just where it's going to be. And the part, and then so then it's going to just have those values in there. We're going to add a further value, so nqt, right? You can see there, and then we put t in there. The size is going to be changed to 3. The rear is going to change to 2 because now instead of being m, it is now t, and then the front is 0, and we don't return anything. Finally, the last thing that you want to have a little look at is dequeuing from a queue. So instead of removing it from there, that's quite a common mistake, is where people think you actually need to take it out of the array. Unless the array is full and it's a circular queue, you're not going to actually be removing anything from there. So that's point number 1, where I see people make lots and lots of mistakes. So leave it in there unless it's a different kind of queue, which I'll do in a later video. The size now changes from 3 to 2. The rear pointer is going to stay at 2, and then the front is going to be 1. And it returns the value. So that's the main thing, is that it's going to return the value, which is y. Now, we're then going to go on to stacks. With stacks, this is everything. So all specifications are going to be using this one. So stacks, as you can see, I'm going to recycle a lot of keywords in this because I'm trying to make it easier for you to remember your flashcards. Make a flashcard for each of these questions. Abstract data type, instead of being a FIFO data structure, it's a LIFO data structure. Last in, first out. The analogy that people always give is a stack of books, and pretend that you can't just take things out from the middle. You take things off the top of the book. So it's the last item that's on the stack of books is the first item that is going to exit the stack. We use operations pop and push, which we had a little look at pop on the last one, but I'll talk about that in more detail. Uses of stack on a computer is undo and redo. Now, how to add data to a stack is we push it onto a stack. So again, you get a mark for that. Check if the stack is full to start with, because obviously if it's full, you're not adding anything on there. And then you add one to the front pointer. How you remove data from a stack is popping, right? And how that works is, on the queue, when we were talking about how we put position 0, which is the front of the queue. Now what pop does is it's actually going to go to the back of, it's essentially the last item in the stack automatically. So if we just don't put a positional value in there, it will remove the last item from it, which works fantastically. It's going to check if the stack is empty. We return the value pointed by front. So essentially that's going to be the item at the front, and then we decrease the front by 1. Okay, so those are the steps in there. Now, having a little look at the code examples, because they may ask you to code this. Push, you put the item that you want to put onto there. Check if it's full. Again, recycling things that we know, make it easier for yourself to revise. It's the same for queue. It's the same for stacks. There are obviously different ways of doing this, but it is just a good idea to remember. It's a good idea to explore other examples, but if time is limited because exams are very, very near, just use my ones. Append it. Very, very, very similar. Size is going to increase by 1. Now, the pop function does already exist. So what we're going to do, so as you can see, we've got pop there. As long as we leave that and we don't put a value in there, that's going to start automatically taking values away from it. And if you create your own little function where it's going to check to see if it's empty to start with, fantastic. Yeah. And then you're just going to decrease the size by 1 if that's the case. So again, nice and straightforward, using a lot of the things that we've done before. Try and recycle as much information. If there is less information for you to remember, it's going to mean that then you have got more, you've got less to revise, which means it's a higher probability chance that you're going to remember all of this stuff. If you've got more to remember, then it's less likely that you're going to remember it, because it's just naturally more. Advantages and disadvantages of stacks. Simple to implement, and you get this thing called a stack overflow. This is where the stack's full and you try to add an item to it. That's quite a common problem, so that's the main disadvantages of those. And finally, let's have a little look at an example of a stack in action. So how you create your stack. We push Mondeo onto there, so you can see there. We push golf on there. You've got is empty, which is just going to check if there's any items in there, and that's going to return false. We push Fiesta on there. We push Punto on there. Then let's say that we add carstack.pop on there, and we just put it, just left it in brackets there. What would happen is that would actually pop Punto out. So that would be the item that would be returned. So it would say carstack.pop brackets, and then we'd have the item would no longer be in the stack, so it would just say Mondeo, Golf, and Fiesta. A lot different to the queue where it stays in there. In this particular one, it would actually physically exit it, and then what would happen is you would it would return that value. So Punto would be returned in there. So let's keep going. So with the hash table is the next data structure that we're going to look at. So hash tables, abstract data type, keep using that word. It shows to the examiner that you've done, you've done your revision, you've done your stuff. You're playing a game and you're trying to make it seem, that you know your stuff. So use abstract data type. It means that you can find and store data almost instantly. This gives us the benefit that we don't have to sort the lists of data, but we also have to do and perform binary searches, which are going to take time, or potentially even worse, a linear search in there if it's an unorganized list. And that's going to save us a lot of time. So we can instantly find the value or put it in the position. The way that we do this, so how we add data to a hash table, is we use a hashing function that will generate you a value from the data. And then I've given a little example underneath there so you'd say you've got 100 items in a hash table and the data that you need to input is 154. You mod 154 with 100 to give you 54 is then stored in position 54. So you use the value to create the position where you're going to store it. So one of the sort of follow-on questions that I see is what happens if you generate data with the same location. This is what's known as a collision, and a collision essentially is where you've got two items with the same data. They might word the question slightly differently, and they might say, what's a problem that you could see happening with hash tables, or what are some of the issues with hash tables? But it's the same answer. It's a collision. The way that you overcome that is you sometimes have to implement a skip, which is where instead of putting them all next to each other, what you do is you can put it like two values away, or 4, 3, 5, however many, and you're just going to simply put them next to each other, but implementing a slightly higher what's called skip factor throughout that. Advantages of hash tables is it's the idea, the big advantage if it asks you for why would you use a hash table in a particular circumstance, is you can instantly search, find data. You don't have to waste time, so it's going to be a lot more efficient using lots of those keywords. Collisions can lead to clustering, so that's where you've got data, lots and lots of data together, and you have a large amount of data in one place, which can slow searching down because it's having to go through lots of different skips, so that can sometimes slow things down. Now, this is the hashing, how we search, and this is going to be appropriate for this because it does actually ask if you can search these, how do you do it? Now, what it's going to do is it's going to obviously apply the hashing algorithm to generate as a value. And then it's going to look there and see if that value is in said position. Now, what's really, really important is if we delete something from our hash table, that we put a marker in there. I think we're so used to this idea that when we delete stuff that we have to physically take everything out from it. But the hash searching algorithm, it's so important that essentially that we're able to go through and check whether there's been a skip value implemented. Say that I delete something from position 3 and that was a skip value. If I don't put anything in there, just a little place marker to say I've deleted something from here, the search algorithm will stop because it thinks it's a blank space and that the item isn't going to be in there. But little do we know that we've actually stored a value 2 on from that. And because it's an empty space, it won't then go on to go and find out more of to go and find out more information on that. So that would just be something that is, I think, is people don't really understand about hash tables, is that when we delete something from there, we have to put a place marker. Now, let's have a little look at an example of how hashing works. So we've got five storage spaces in this in this hash table, and we've got some values that we're going to store in there, and you can see how this works. So we mod it with the number of positions, so 5, and that generates as a position of 4. We store 14 in there. 27, when we mod that with 5, we get the remainder of 2, so we're going to store that in position 2. 17, we mod that with 5, that gives us 2 again. Now this is where we've got our first instance of a collision. So what we do is we implement a skip and we put it next to it. And then you can see 44, that gives us a position of 4, which 14 is already there, so we implement a skip and store that there. And they may just get you to do an example like that. Final one is, how do we actually program this? We use a dictionary. So this is how you implement a dictionary. I just made up some like class scores where you've got like an index and then you've got some values. I just made it up. And let's say that you wanted to actually add some items to it. So you get a score, use the position, we mod it, pretend, there's 100 data structure, 100 items that we can store in there. We mod it there. And then what we do is we store the position in there. And then what that'll do is that'll add whatever we've stored in there to class scores. So the position goes, whatever it is that we've decided that is the position, the number on the left. And then score is just going to go on to the right. Graphs is the next data structure. So we've got 2 left. Graphs, abstract data structure, is our favorite term for today. It's a set of vertices and nodes connected by edges and arcs. I'm going to show you what that means in a second. Satnavs are use graphs. They can be undirected, directed, weighted, or unweighted. And here, as underneath, we've got the uses: Satnavs, AI, machine learning networks, web page rankings. There's loads of different examples on there, just so that you can see an example of these. So it's made up of nodes and edges. We've got the different weights on there as well. So as you can see, it's just got a node, it's got edges, and it's got edge weights. And that's essentially what a graph looks like and some of the different features of them. Now, with the kind of questions that I've seen come up with graphs, is they try and get you to represent them based on adjacency, matrices. Matrices actually is the plural of that. But so let's have a look at how we do that. And you can see on here, we've got the different nodes, and this is a directed but unweighted graph. So it hasn't got any line weights on it, so I don't need to write those in there, but it has got which direction the data is going to flow from it. And it doesn't give us any, it doesn't tell us what it's about, but it's just saying here that this is the direction of where it's going. So if we have a little look here, where do we put it? Because the where people get confused is like what position. It's like the A is going to the C. Like where do we put that? So as you can see, it's not A to C, top to bottom. We go this way, so A to C. So we put the 1 there. So if it's directed, you're going to go along this side here, and then you're going to put the position there. And then B, if we have a look at another example here, so you put B and that's going to go there. So you don't put it the other way around, because you could go A to C, but that doesn't work in this particular case. Now, when it's undirected and weighted, obviously we have to put them in both instances. Some people only do one half of it and they don't get half the mark, so that's a little bit annoying. But what you would do here is you're going to do A to C, so 7, A to C. So just make sure that you cover both bases. And that's pretty much it, on those ones there. So just making sure that you do all of those ones, because you have to do both sides of it and it's got to match up. So yeah, you've got all of those there. Advantages and disadvantages of using adjacency matrices or matrix. It's convenient to work with, and adding an edge is simple if you do this. A sparse graph with not many connections, it's going to leave a lot of cells empty, so it can actually leave a lot of wasted space in memory, so that's a bit of a disadvantage, which you could then use an adjacency list to compensate for that. An adjacency list is just another way of doing it. And all it is you've just got your nodes, and then you just point through to where the different values are going to go to. So A is going to C, so that's why we've got that there. And so B is going to go to C and D. So this is a directed but unweighted graph on this one. Here, what we've got is is the undirected weighted graph. And as you can see, we've got to cover both sides now then, because obviously A is going to C, and then you just use the 7 there. And then we've got, so the C also has A, doesn't it? Because the weight is 7. So you put the little colon and then you put the weighted value there also. So it's just about knowing, have you got it weighted? Have you got it directed, undirected, whichever side it is? And then just knowing all of the different ones. Have a flashcard of these and just practice, like, what do I do if it's a weighted graph? What do I do if it's an undirected graph? If it's an adjacency list, if it's an adjacency matrix. Advantages of this, very space efficient, so essentially the inverse of the other one. It's a really good way of representing sparsely connected graph. And I think this is the last data structure that we're going to have a look at today, which is trees. So trees, abstract data type. It's made up of a set of nodes that can either be root, parent, or leaf nodes. An example of a graph which does not have a cycle. Yes, I'll show you about that in a second, actually. It is technically a graph, but doesn't have a cycle. That's the important thing, and I'll show you what I mean by cycle in a second. File directories, and it's really good for machine learning algorithms and all sorts. As I said, there's loads of these, but just a couple of quick examples for you. So can you see what it means by a cycle? Can you see on this one up here that we can get round? So it's cycles. We can go to the different values. Here it goes down, it grows depth, so it finishes that. F doesn't then just link up to H or I, so that's how it works in that case. And you can see some of the key terminology in there. Some of the 1 mark, 2 mark questions is they will get you to define what some of these key terms mean. So for example, what is the root node? What is the leaf node? So they're just the ones at the end. What are the parent nodes? What is the subtrees? So the subtrees are just either side of it. So you've got a left subtree and a right subtree there. The edges. So yeah, some of the key terminology. I just thought, why would you use this over a graph, essentially? An advantage. Simple to implement. It's a hierarchical structure. It makes searching much easier. Now, this is so common that they chuck in a traversing. So traversing just means, like, how do you search it? Okay, so what is it that we're doing? So there's pre-order, in order, and post-order. Flashcard on each of these, go over it until you can remember it. So if we take this tree as an example, we'll just have a look at the ones on there, and I've put a little note in there just to where I see lots of students get things wrong. So it says so it goes in this order. So this is pre-order, by the way. So it starts with the root node and then goes F, D, B, A. So it goes down the left subtree, and then it's B, A, and then C. We're still on the left subtree, and then it's going to go. So some people then are confused and they're like, where do I go from now? Do I go to the bottom of the next one? That you then go to the top of the next right hand side subtree. So let's say you had 3, you'd go to the one in the middle. In here we only have 2, so you're going to go to H, G, keep going left as much as you can, and then J, and then Z. So lots of places where people get things wrong is from the G, they might be tempted to go to Z. Don't do that. So that's how we do the pre-order one. In order one is you're going to start off so A, B, C, D. So with this one here it's A, B, C. So the way I think probably the way of thinking about this is you're going left to right. So it's as the values. So if you're starting from the left hand side and going from over to the right hand side, you're just going to work your way along, and it's A, B, C, D. Yeah. So in order is probably the easiest one to remember because you're just going left all the way across, and that's quite a nice way of thinking about it. Post order. So you start off with A. So you're going to go A, C, B. So and then you're going to go D. Now, here where I see a lot of students get things wrong is they would maybe think that F. Just remember that you essentially start on the root node. Oh, I spelled root wrong there. I was rushing to try and get this out because exams are really, really short, so sorry about that. But yeah, root node there. So we've got so it's going to go A, C, B, and then it's going to go D. Now, place where people get a little bit confused on this one is where to go next after this. You then go to the bottom left-hand corner of the next subtree, so G, and then you're just going to go Z, J, H, F. And it's so important that you get the order right because either you don't get any marks, so going through like that. Okay, last little point then is building a binary tree. So building a binary tree, essentially, how this works is you've got the 12 up at the top, and this is the first item we're going to put there. And then what you do is you progressively keep asking the question for the next item: is this bigger or smaller than the value that I've just put in there? So is 7 bigger or smaller? It's smaller, so it goes to the left. If it was bigger, it goes to the right. 18 is bigger, it goes to the right. Is 22 bigger or smaller than 12? It's bigger. Is it bigger or smaller than 18? So it goes to there, and then we've put it there. Is 14 bigger? Is it bigger or smaller than 18? 14, and then you built up the whole binary tree by that point then. How do you delete an item from a tree? So go to the parents node and change the pointer of the leaf node to null. So again, some nice, just simple, just flashcard. Remember the definitions, just go over that lots and lots of times. How do you add an item to a tree? Go to the parent node and change the pointer of the leaf node to the value of where you have stored the leaf node data. E.g., 5 is stored in position 10. Parent pointer points to position 10. How do you search a binary tree? So with this one here, I've tried to write down an example here. So you go to the root node and compare it with the value you are looking for. If it is the value, you stop the search. If it isn't, so I might try and bullet point this for you actually, because it might be a bit easier if that. So if it is the value, you stop the search. If it isn't, you ask, is the value bigger or smaller than this? And then go to the left if smaller, or right if bigger. Repeat the process until you either find the item or get to the end of the tree and report the item is not in the tree. So those are the points there that I would strongly. I've probably gone a little bit over what we need there, but it just fully explains how you go for it. So say if I was looking for 7, I'd go, is 7 12? No. Is 7 bigger or smaller than 12? It's smaller, so I go to the left-hand side. Then go, is 7 7? Yes, and then I say it's in the list. If I put an item that wasn't in the list, then I would just go through the whole thing, and I get to the bottom and it'd be like item not in list. And those description points there are perfect for that. People, I hope that was useful. I tried to condense so much information really, really quickly for you there, and best of luck.